practice question 4. I think this is another good possibility because I think there's a lot in here. You're presented with two different functions, f and g, and here we have the graph of f prime, but we know that f of 0 equals -2, so beware, FTC is coming at you. Tells you two line segments, so the fact that we know it's two line segments means areas and slopes and all kinds of fun stuff. And then for g of x, we have a table with some values for g, g prime, and g double prime. Remember, this is only some values. That's going to be important too. So part A, when does f have a relative maximum, and give a reason? Well, if this is the graph of f prime, relative maximum happens when f prime goes from positive to negative. So there we have it at x equals 2. So a relative max at x equals 2 because f prime changes sign from positive to negative. Part B, when does g of x have a relative minimum? Now everybody wants to jump right away and say g of x has a relative minimum at x equals 2. At x equals 2 because g prime is 0 and there's a sign change. But there is no sign change. We don't have enough information. And technically we're going from negative to 0 to 0 and then back to negative. So really there's no sign change and we don't know what's going on in there. So this is where we have to use, yes, there is a relative minimum at g of 2 because g prime of 2 equals 0, but now we use the second derivative test. G double prime is positive. If our function has a second derivative that's positive, it means it's concave up. And when you think about a concave up function, what does that have? It has a relative minimum. So you just have to say because g prime of 2 equals 0, g double prime of 2 is positive, we have a relative minimum by the second derivative test. Now we go to part C, an expression for f of x that includes an integral, and then use that expression to find the values of f of 2 and f of 5. Here's where we use FTC. Any value of x minus f of 0. Why are we using f of 0? Because that's the value we know is going to be the integral from 0 to x of f prime of t dt. Remember, we can't use x inside the integral. We're integrating with respect to x. That's how we're going to get our f of x value. So we use a dummy variable in there. It could be f prime of t, f prime of g, whatever variable you want to use. And then we need that to evaluate f of 2 and f of 5. So what I did here, we said, okay, there's the initial one. Now we're saying f of x is integral from 0 to x of f prime of t dt. And remember, f of 0 was -2. So this would be minus a -2, which would make it +2. But when we move it over, it becomes -2. And now we use that to evaluate f of 2. So integral from 0 to 2 of f prime, and then -2. Well, from 0 to 2, we have that triangle, 1/2, 2 times 2. And then -2 gives us 2 minus 2 is 0. F of 5, integral from 0 to 5, and then again, minus the 2. So we start off with our triangle above, 1/2, 2 times 2. Minus the triangle below, 1/2 of 3 times 1, and then -2. So we have 2 minus 3/2 minus 2 gives us 1/2 minus 2, which is -3/2. So there's our part C using FTC. Part D, here we go again with an absolute minimum. Okay, absolute minimum or maximum are going to be at an endpoint or at a relative minimum or maximum on the interval. Okay, and we're looking from 0 to 6. So we have to find f of 0, f of 6, and we look at our graph for f of x, and we have to look at f of 2 and f of 5 as well. So we say, okay, f of 0 we got was -2, f of 5 we got was -3/2. F of 2 was 0, f of 5 was -3/2. F of 0 we know is -2, they gave that to us, so we just have to find f of 6, doing what we did in part C with 6, and again just doing our areas, and we get -5/4. So we look at our values and we say, okay, which is the absolute minimum, the absolute smallest value there is -2. And again, it's asking for the absolute minimum. We just give the y value, we don't need the x. Part E, we want to know, is there a value of c such that g prime of c equals -2? If so, explain your reasoning. If not, state that there is no such value. It does say that f and g are differentiable, so that means our mean value theorem holds true, and we're looking at the interval from 0 to 6. Is there a value of c such that g prime equals -2? Well, we could do from 0 to 2, we could do from 4 to 6. Either way, when we sub in, we're going to get -2 when we use our mean value theorem. So we have to say, since g of x is differentiable, it's also continuous, so the mean value theorem holds. Since 0, 2 is part of 0, 6, and g of 2 minus g of 0, we get -2 by mean value theorem. There must be a value c on the interval 0 to c to 6 such that g prime of c equals -2. I think somebody actually used intermediate value theorem for this, but now that I think of it, we do not know that g prime of x is continuous, so we cannot do intermediate value theorem here. If we knew g prime was continuous, intermediate value theorem would be a real easy one to do, but it does not tell us that g prime is continuous. So, just something to think about. Part F, here we go, limit, probably going to be L'Hopital's again, right? So the limit as x approaches 2 of f of x over g of x becomes f of 2 over g of 2. F of 2 we found out up above in part C was 0. G of 2 we have in our chart is 0. 0 over 0 means we do L'Hopital's. So we do the limit as x approaches 2 of f prime of x over g prime of x. F prime of 2 is 0 from our graph. G prime of 2 is 0 from our chart. So again, we get 0 over 0. So now we can do the limit as x approaches 2 of f double prime of x and g double prime of x. F double prime of 2 is the slope of f prime at x equals 2. And when we look at that graph, we see the slope is -1. G double prime of 2 we get from our chart is 2. So our final answer here is -1/2. Remember, you can use L'Hopital's. If you keep getting 0 over 0, you just keep going. Okay.